Hey guys, welcome back to Food for Thought Physics, where today we're going to be talking about the force of friction. Friction is the main force responsible for the deviation of the ideal world that Newton, Galileo, and others envisioned, where objects keep their velocities indefinitely, from our real everyday world, where you might know pushing an object or otherwise exerting a force on it and accelerating it only gives it a forward velocity for a brief period of time. This is due to friction. Friction is caused by the imperfections between two surfaces when they try to slide against each other. Because in the real everyday world, no matter how smooth some objects might seem, if you zoom in far enough, you're going to see all these jagged bumps and ridges, which are going to interfere with two surfaces' ability to slide against each other. There are two types of friction: static friction and kinetic friction. We're first going to examine what static friction is. So static friction is going to be the friction between two static or non-moving objects. As an example, here I have a block on the ground where there's going to be friction between the block and the ground, and someone or I am exerting some force F again on this block from the left, and I'll be pushing to the right. And let me actually quickly add this vector hat right here. So static friction is what happens before these objects move. So for instance, if my applied force, my F here, is very small, then there might be too much friction and the block is not going to move. So static friction is going to be some force which occurs between the ground here and the block. And I'm going to draw this in orange. And it's going to counteract the movement of this block. And sometimes, often we denote this friction with a small f, and we're going to put a subscript s for static friction. And here the static friction is going to equal F, except in the other direction, or rather equal negative of this force, because it is perfectly counteracting this force. But static friction does have a maximum value. We can't just keep pushing and the friction is just going to keep stopping us. At some point, no matter what objects they are, we're going to be able to move it. So the maximum value of this static friction, so I'm going to write the static friction here, this F sub s, is going to be less than or equal to the normal force on the object, so it's proportional to the normal force, multiplied by this mu sub s. And this mu sub s here represents what we call the coefficient of static friction. And the coefficient of static friction depends only on the materials of these two objects, not on the surface areas, not on really anything else, just the materials made between these two surfaces. So if you take any two surfaces, you can experimentally calculate or search up some coefficient of static friction. And as long as your applied force is less than this F sub n times mu sub s, the static friction is going to equal F, and it's going to counteract this movement. It's going to always go opposite your applied force. Once it's greater, though, the static friction stops, and it's going to start moving. And here, this friction is going to become what we call kinetic friction, which is the friction between two moving objects. So now basically what we're saying is that this force is strong enough that this object is going to start moving. We've overcome the static friction. Our force is greater than this normal force times the coefficient of static friction, and this object is moving. Once the object starts moving, the friction force is going to change. It's still going to act against this applied force. It's actually going to act against the velocity of the object now, but the actual F sub k. So we're going to call this F sub k. So friction force sub k. So kinetic friction, and the value of this kinetic friction is now always going to be the same thing, no matter how much your applied force is. The magnitude of this friction force is now always going to be equal to the normal force, of this surface against this surface, multiplied by mu sub k, which is going to be the coefficient of kinetic friction between these two objects. And again, we can experimentally determine this through based on just the materials of these two surfaces and nothing else. But we might say, why are there two different mu's here? Well, because for any two surfaces, or pretty much any two surfaces, mu sub s and mu sub k are going to be different values, and they're just a dimensionless coefficient that affects the friction force, but they're going to be different values for any two objects. And in pretty much all cases, we're going to have that this mu sub k is going to be less than mu sub s. So based on this, we can and this is due to the fact that while these objects aren't moving, all these mountains and hills and whatever are going to be locked into each other like teeth. So it's going to be really hard to get them to start moving. But once these objects do actually start moving against each other, these mountains, these ridges, whatever, are going to start bouncing against each other. And since they won't get locked in like they were before, there's now a lot less, or not necessarily a lot, but there's now some amount of less force that's going to be trying to impede this motion. So the friction force is going to decrease. So we can draw a graph of the applied force versus the friction force to try to see how this works. So if we have our two axes here, and I'm going to make these axes kind of weird, but the x-axis I'm going to put as the magnitude of the applied force, while the y-axis is going to be the magnitude of the opposing friction force. So essentially, at first, while our force is still less than the static friction, which I'm going to label as, say, right here, this right here is going to be our F sub n times mu sub s. The resulting friction force will be the exact same as this applied force. It can't be greater. It can't always have this max value, or else there would be a net force going backward. And we know blocks don't just magically move backward on their own, mostly. So as long as we're less than this F sub n times mu sub s here, we're going to have that the force of friction is going to equal the applied force. It's going to perfectly counteract it, and the block is not going to move. However, once we get to this breaking point right here, this is going to change. I'm also going to label this right here, this F sub n times mu sub k, because remember, this mu sub k is going to be smaller than the mu sub s, so it's going to be less than that. So at this point, once we get to this static friction value, or this maximum static friction value, we're going to be overcoming this static friction. The block is going to start moving. These ridges are going to start bumping against each other and bouncing off each other, which causes less friction. So now suddenly the friction is going to drop to here, to this constant F sub n times mu sub k, this normal force times coefficient of kinetic friction value. And there's now no more static friction, there's only kinetic friction, which is going to be constant no matter how much we raise F. And that's going to continue on. So this here is just a brief introduction to how friction works. We have static friction, which is between two objects that are not moving against each other, but rather opposes any attempt to move them, and kinetic friction, which is going to occur between two moving objects. And this kinetic friction is going to be what slows down objects that are already in motion. So now that we've covered pretty much all of the basic mechanical forces, in the future videos we're going to start analyzing various more specific situations using these forces and develop some equations and solutions for these specific situations that we're going to encounter in many of our problems.